Good day and welcome back for the fifth and final part of our discussion on integrating rational functions. As I indicated at the end of our previous video, you can find an associated class worksheet on Canvas. Hopefully you've located that worksheet and you've invested some time into working the problems. In this video, I wanted to summarize problems 1C and 2A. In problem 1C, we're essentially asked to come up with a partial fraction decomposition. But note, this is an improper rational function. The degree in the top is equal to the degree in the bottom, which indicates we somehow need to rewrite this algebraically. And I'm actually going to go through two different approaches. The first approach is to just think about it intuitively, whereas our previous approach was to do a polynomial long division. So let's think about this from the more intuitive perspective. If I was to allow you to add or subtract some number in the numerator to make this fraction as simple as possible, what number would that be? I'm guessing you would say a -1 would be extremely helpful. But we can't put a -1 for free, though we can certainly add 0, -1 plus 1. And then break it up into two fractions. You have the first part, x to the fourth minus 1 over x to the fourth minus 1, plus the second part. So we would have 1 plus 1 over x to the fourth minus 1, which, as we will see in a moment, is exactly what you would get with a polynomial long division. And I'm going to write out the form of the PFD. We need to factor the denominator in the second term so that it involves irreducible quadratics and linear terms. Note, x to the fourth minus 1 is really a difference of squares. It's x squared minus 1. And whenever we have a difference of squares, we can factor this as x squared minus 1 times x squared plus 1. X squared plus 1 is an irreducible quadratic, whereas x squared minus 1 is also a difference of squares. So x minus 1, x plus 1 times x squared plus 1. And without writing anything else down, we should be able to look at this term and immediately indicate how many terms the PFD will contain and how many constants. And the answer is it will contain 3 terms, 1 for each factor, but 4 constants, 1 constant for each linear term and 2 constants for the irreducible quadratic. And the form of our PFD is a over x minus 1, b over x plus 1, and then a cx plus d all over x squared plus 1. And I do want to go back to our initial step. Remember, we thought about this from a very intuitive perspective to rewrite it algebraically. Another perfectly good approach would involve a polynomial long division. That is, take x to the fourth minus 1 and divide it into x to the fourth. And we simply ask ourselves, x to the fourth multiplied by what is x to the fourth? And the answer is 1. So we subtract away x to the fourth minus 1, and what we're left with is 1. And this makes perfect sense, because what it's telling us is if we multiply together x to the fourth minus 1 and 1, and add the remainder, we get x to the fourth. So x to the fourth minus 1 times 1 plus 1 is x to the fourth. And if we divide each and every term by x to the fourth minus 1, we're left with the function that we are hoping to rewrite. So putting this all together, we have 1 plus 1 over x to the fourth minus 1 is x to the fourth over x to the fourth minus 1, which is precisely what we saw earlier. And it's always worth reminding you that there typically are multiple ways to do a given problem, and it's rarely about there being a right way or a wrong way. As long as you are using mathematics that fit within the scope of our class, it's usually more about finding the way that you understand or the way that's more convenient for you. Let's now move on to 2a. In this case, we're asked to evaluate an indefinite integral. And note at this point, it's no surprise that we are going to use a partial fraction decomposition because it's a proper rational function and none of our previous techniques would apply. There's no obvious substitution. I don't think I would want to try integration by parts, and there's no trig substitution that jumps out at us. So the only real choice is to do a partial fraction decomposition. This requires us to factor the denominator. Note you can pull an x out and have 3x squared plus 4x minus 4. And then note this also even factors to give us 3x minus 2 times x plus 2, which we could certainly distribute out and verify. So in terms of the PFD, this algebra we have to do to the side, 3x squared plus 4 divided by x times 3x minus 2 x plus 2 is, believe it or not, the ideal scenario. Whenever we only have linear terms involved that are not repeated, all raised to the first power. This is the quickest, most efficient type of PFD we can determine. So we would have a over x plus b over 3x minus 2 plus c over x plus 2. Take the denominator on the left and multiply through by it. In the first term, the x's cancel. In the middle term, the 3x minus 2's cancel. And in the third term, the x plus 2's cancel. And now, by substituting in an intelligent choice for x, we can immediately determine all three of the constants. So if you have not done so already, I would like you to pause the video and determine those values. So going ahead and writing out a bit of the work, if we would like to solve for the constant a, we can simply substitute in x equals 0. That turns the b term and the c term into 0. And we're left with 4 equals a times minus 4. So immediately we would have a must be minus 1. Similarly, to solve for the b, we can substitute in x equals 2/3 to make the a term and the c term vanish. So when we substitute in x equals 2/3, we're left with on the left 4/9 plus 4, and on the right it's b times, when we multiply these together, 16/9. So here we need to do a small bit of algebra. 4 is 36/9, so we have 40/9 equals b times 16/9. So if we multiply both sides by 9 and divide both sides by 16, that would leave us with b being 40 over 16, which is really equal to 5/2. So b equals 5/2. And then finally, to solve for c, note x equals minus 2 makes the first two terms vanish, and we're left with on the left 8, and on the right we would have c times minus 2 minus 8. So in this case, note the two minuses on the right become a positive, and when you divide 8 by 16, you're left with c being a positive 1/2. And we very quickly have determined the partial fraction decomposition. So let's go back to this original question. We wanted to integrate the function x squared plus 4 over 3x cubed plus 4x squared minus 4x. So just rewriting the PFD, we would have a over x plus b, so 5/2, over 3x minus 2, plus c, 1/2, over x plus 2. And if we would like to integrate this, we could really just break it up into 3 separate integrals and integrate each term individually. So I will leave the finer details to you, but this is minus the natural log absolute value of x. In the middle term, 5/2 pulls out front. Because of the 3 with that x minus 2 in the bottom, we would have 1/3 natural log absolute value 3x minus 2. And then for the final piece, 1/2 natural log absolute value x plus 2. And note, as usual, there are plenty of good suggested problems and more problems on this worksheet for you to consider. So as you're practicing, if you have questions, do not hesitate to reach out. And at this point, we've actually finished discussing the key techniques of integration that we are going to be looking at. And the next section we are going to investigate is on strategies of integration. That is, we will dive into the thought process or the mindset that will help us determine the technique of integration that will work the best for a given problem. Stay tuned. Take care.